It's never been anything but that balance, and we've complicated it with a lot.
The European Organization for Nuclear Research, CERN, is home to scientists who are working to find an answer to history's most important issue. Ever wonder what materials make up the universe? Are you able to do this? Simply by colliding particles in a device known as the Large Hadron Collider, LHC, at extremely high speeds. The LHC can observe even the smallest particles in the cosmos, much like a massive microscope. But an odd incident happened in July of 2022. Something unexpected was picked up by the LHC as an anomaly. What was the unusual occurrence? What may that entail for us? And is there any cause for concern? All you have to do is listen through to the very end to find out. The European Organization for Nuclear Research, CERN, unveiled the world's largest particle physics experiment, the Large Hadron Collider, LHC, in 2008. This massive subterranean apparatus operates beneath the French and Swiss borders. With its ability to smash particles together at extremely high speeds, the LHC has proven to be an invaluable instrument for scientists, providing fresh insights into the fundamental elements of the cosmos. Notwithstanding its achievements, the LHC suddenly ran across an unforeseen issue. At its maximum energy, the LHC yielded an incomprehensible and mysterious result. Scientists are puzzled by this phenomenon and making assumptions about its origin and its consequences. What may this aberration signify for our comprehension of the cosmos, and why did it occur? In what ways may it impact scientific research going forward? Researchers are now attempting to find answers to these issues. A multinational collaborative vision served as the foundation for the LHC's journey. Scientists and decision-makers in Europe realized that collaboration was essential to advancing scientific research following World War II. Physicist Louis de Broglie's 1950 proposal for a common European laboratory resulted in the establishment of CERN in 1952 by 11 nations. On the French-Swiss border, CERN was founded in 1957 with an emphasis on atomic nuclei research. In the 1980s, the idea for the Large Hadron Collider, LHC, was born out of the need for a more potent instrument to unlock the secrets of matter. In 1998, a multinational team of scientists and engineers began construction. Far exceeding prior records, the LHC achieved its first particle collision by 2010 at 3.5 TeV per beam. It is now operating at 6.5 TeV per beam following many modifications. High-speed particle collisions take place at 4 distinct sites, which are observed by 7 detectors intended to record the resultant events. The LHC mostly collides proton beams, although it also concentrates on heavier ions, such as lead, once a year. Scientists may investigate hypotheses like the Higgs boson and supersymmetric particles thanks to these tests. There have been challenges along the way for the LHC, such as a significant magnet malfunction in 2008. However, it has produced important discoveries, including the 2012 discovery of the Higgs boson. With planned future modifications, the LHC, now in its third phase that will last until 2025, is primed for even more discoveries. On July 7, during its third cycle, something amazing happened. For 14 hours, a gap in Earth's magnetic field allowed solar winds to produce geomagnetic storms and breathtaking auroras. This was ascribed to a lengthy geomagnetic storm caused by a co-rotating interaction region, CIR, from the Sun. Europe lay in ruins after World War II, and scientists and decision-makers realized that cooperation would be essential to reviving science. Physicist Louis de Broglie proposed in 1950 the establishment of a common European laboratory to foster scientific progress and peaceful coexistence. The CERN Treaty was signed by 11 nations by 1952, and CERN was founded in 1957 near the French-Swiss border. Studying atomic nuclei was CERN's primary objective, necessitating the use of strong devices known as particle accelerators. By accelerating particles to almost the speed of light, these accelerators allow scientists to discover the universe's fundamental elements. The concept for the Large Hadron Collider, LHC, began to take shape in the 1980s when scientists realized they needed a more potent device to delve deeper into the secrets of matter. The LHC, which has a 27 km ring of superconducting magnets and detectors, was intended to be the biggest and most potent particle accelerator in the world. Commencing in 1998, the LHC's construction was a tremendous technical achievement. It took 10 years to complete and engaged thousands of scientists and engineers from all over the world. It was located 100 meters below the surface. The LHC was prepared to begin experiments in 2008. By burying it below ground, expenses and land area were reduced while protection from outside disturbances and the challenging Jura Mountain topography was maintained. At an energy level of 3.5 tera-electron-volts, TeV, per beam, over 4 times the previous world record, the LHC produced its first particle collision in 2010. It now runs at 6.5 TeV per beam following additional enhancements. 2 particle beams are accelerated to almost light speed at the LHC and then collide. There are 4 distinct locations where these collisions occur, and 7 detectors are positioned around each to observe the phenomenon that results. The Large Hadron Collider, LHC, is an enormous scientific device used to examine the tiniest particles in the cosmos. It is comparable to a massive microscope. It runs continuously throughout the year, mostly clashing proton beams. But once a year, it concentrates on heavy ions like lead for a full month. This yearly occasion gives scientists the chance to carry out investigations into some of the most intricate and fascinating hypotheses in particle physics. Why is so much work being done? It all comes down to our innate curiosity for the cosmos and its basic elements. Testing. Hypotheses like the existence and characteristics of the Higgs boson, which was notably proven between 2009 and 2013, depends heavily on the LHC. In addition, researchers utilize the LHC to look for new particles that might be explained by supersymmetric theories and provide light on the enigmatic dark matter that makes up a large chunk of the cosmos. Hadrons, which are minuscule particles made up of even smaller particles called quarks, are the fundamental units of study at the LHC. These quarks function similarly to the protons and neutrons that make up the nucleus of an atom. The Large Hadron Collider, LHC, smashes these particles together at extremely high speeds to replicate circumstances that existed just after the Big Bang, providing a fleeting window into the early cosmos for scientists. In terms of engineering, the LHC is a masterpiece. Constructed between 1983 and 1988 within an expansive subterranean tube with a width of 3.8 meters and many concrete layers for protection, a complex of structures situated above ground beside the tunnel contains the necessary equipment for running the collider. This comprises strong compressors, cooling mechanisms, ventilation systems, and sophisticated control electronics. These components are essential to keeping the LHC operating at the forefront of scientific inquiry. The LHC's voyage has not, however, been without difficulties. Its activities were put on hold for more than a year in 2008, following a severe setback caused by a catastrophic malfunction in one of its magnets. The Higgs boson, a long-theorized but never observed particle, was discovered at the LHC in 2012, despite this setback. The particle surged back to life. This finding was a tremendous accomplishment that confirmed the validity of the standard model of particle physics and offered vital new understandings of the underlying forces governing the cosmos. The LHC restarted operations in 2015 after a number of maintenance and improvement initiatives, and it did so until 2018, when it once more went into a scheduled downtime and refurbishment phase. With a beam energy boost of 6.8 TeV, the LHC commenced its third operating phase in April 2022, with a projected duration of 2026. The European Organization for Nuclear Research, or CERN, hopes to gather even more data and produce more groundbreaking discoveries during this time. The prospects for particle physics appear bright when looking ahead. The LHC is ready to keep pushing the boundaries of what we know, from examining the nature of dark matter to examining the basic characteristics of particles and forces. Huge volumes of data are produced by each collision at the LHC, which scientists painstakingly examine using advanced detectors and computer programs. By revealing fresh information on the most fundamental interactions between matter and energy, these analyses contribute to the discovery of the universe's mysteries. This is when things really start to get exciting. The LHC generates around 15 petabytes of data annually. That's an enormous quantity of data. A global partnership established a computational grid specifically for the LHC. This network is a miracle unto itself. Finding the answers to the riddle surrounding the Higgs boson, a mystery particle, is the primary objective of the LHC. Although scientists had anticipated it, this particle had never been observed. Its large bulk made it extremely difficult to locate. Several of these Higgs bosons were intended to be produced every minute by the powerful LHC. It's similar to setting up a trap for a rare animal that has never been found but is thought to exist by many. However, the LHC went on from there. In addition to searching for the Higgs boson, it investigated other unexplored areas of physics. It looked for supersymmetric particles as well as other cosmic mysteries. It wasn't all plain sailing either. In 2008, not long after it opened, the LHC had a significant setback. Numerous collider components were harmed by a magnet problem, which caused the testing to be delayed for more than a year. However, the LHC produced several groundbreaking findings once it began to run in 2009 and 2013, including the ultimate detection of the elusive Higgs boson. Following a successful initial run, the LHC was put into slumber for maintenance. In 2015, it returned to the Internet, eager for new experiences. After a hiatus until it resumed in April 2022 with an enhanced beam energy of 6.8 TeV, its second run ran from 2015 to 2018. We will be enthralled by this machine's third run until 2026. However, on its third run on July 7, something remarkable occurred. Consider the magnetic field of Earth as a bubble that protects our planet. That day, this bubble developed an enigmatic fracture. It was not only a temporary error, it was operational for an astounding 14 hours. Imagine the sun as a powerful river that is continuously gushing energy. The sun occasionally releases strong energy bursts that resemble river rapids. Similar to when two rivers combine to make an amazing waterfall, these bursts cause brilliant light displays known as auroras to appear when they strike Earth. One of these bursts hit with Earth's magnetic field during the peaceful early hours of July 7, leaving a persistent tempest of lights in the sky. Because this storm was preceded by another solar flare, scientists from the National Oceanic and Atmospheric Administration, NOAA, observed that it was significantly stronger. Should these occurrences worry us? Not really. Like a strong shield, Earth's magnetic field often withstands periodic outbursts. There could be cracks, but they usually mend fast. But as recent events have demonstrated, these fractures can occasionally persist for hours, much like a window that refuses to close after a storm. A little amount of the storm's energy still gets through even if the majority of it is blocked. Our electrical systems, radios, and satellites may all be affected by this. Don't worry, though, although these disturbances might be annoying, they can also bring forth breathtaking surprises, like as the breathtaking northern lights that Americans and Canadians have been witnessing during this celestial event. Scientists have found that the sun is more active than they had predicted, which indicates that we will be receiving more frequent radiation bursts. Thus, you're in luck if you've ever desired to view an aurora. The likelihood of seeing this amazing natural spectacle within the next 3 years is higher than ever. It appears as though the heavens are preparing for a spectacular color dance, brought forth by our energetic Sunday uncovering the mysteries of the Higgs boson, was one of the astounding findings achieved by the LHC in July 2017. By the year 2021, it has discovered 59 new hadron particles. Subsequently, in July 2022, it detected an entirely new particle composed of a distinct mixture of quarks, known as the pentaquark. However, even the much-loved LHC has problems. Its capacity to provide groundbreaking discoveries may diminish over time. That is the role of updates. As of June 2018, it is receiving a substantial upgrade known as the High-Luminosity Large Hadron Collider. This upgrade will supercharge the LHC, increasing its capacity to detect uncommon cosmic events. For what is the LHC renowned? Well, it found the elusive Higgs boson on its maiden run. We have learned even more about this particle from the second run. Now that the third cycle is scheduled to conclude in 2025, CERN scientists anticipate having twice as much data and maybe twice as many discoveries by 2029. Particles will be colliding at 10 times the speed of light at the LHC after extensive preparation. However, the fun doesn't end there. 10 times greater data sets than what will be available at the end of its third run will be gathered during this phase, which is anticipated to last until 2042. Let's now discuss proton collisions. Protons can be thought of as multicolored jelly bean sacks. Smaller particles known as quarks are contained inside these bags and are kept together by even smaller particles known as gluons. Most of the time, jelly beans disperse when two bags of them crash against one another. However, occasionally a head-on collision between two quarks or gluons causes all of their energy to condense into a single point before exploding. The problem with the LHC is that protons collide at an astounding 40 million collisions per second. Imagine attempting to freeze a special moment from an endless fireworks display, where every shot produces a picture that is 20 times larger than what you could photograph with your phone. Similar to attempting to locate a needle in a haystack. So how do scientists make sense of all this information? Like a careful photographer selecting the best photographs, a clever computer system only chooses the most interesting encounters. These are the times that scientists examine thereafter in an effort to solve the greatest mysteries of the cosmos. The current primary goal of the LHC is to find previously unseen subatomic particles that may hold the key to unlocking new cosmic riddles. Some of these particles break down into smaller particles with enormous energy, like champion boxers. They are the super heavyweights of the cosmos. On the other hand, these heavyweight particles might not be directly detected by scientists during the third run of the LHC. Rather of focusing on locating the actual wealth, they aim to spot hints or glances, similar to discovering a map during a treasure hunt. These indications may open the door to more significant findings in upcoming runs. Dark matter now enters the picture. That strange material that is mostly invisible yet makes up our cosmos is definitely something you've heard of. Although they are so elusive that they seldom manifest themselves directly, certain new particles found at the LHC may have some connection to dark matter. It's similar to attempting to see the wind, although you can't, you may perceive its effects, such as the rustling of leaves. Scientists search for additional particles that travel abnormally at the LHC, which might indicate the existence of these unseen particles. But it's hard to find these subtle indicators. It's like trying to hear a whisper at a rock concert. Upgrades to detectors are underway for Run 3 of the LHC to improve their ability to detect these tiny clues. But there's still more. A larger device, called the Future Circular Collider, is being planned. Consider it the larger brother of the LHC, a colossal particle smasher with a potential price tag of $21 billion to $9 billion. Not everyone, though, concurs with this notion. Some contend that considering the enormous cost, we need to look at other ambitious scientific endeavors, such as building a massive radio telescope on the moon's far side or putting a space-based gravitational wave detector in orbit. Famous physicist Sabine Hossenfelder wonders if the secrets we're seeking to learn will be revealed by this new enormous machine. It's comparable to purchasing a powerful telescope that might not reveal any new stars. The LHC is getting ready for a third and maybe a fourth run in spite of this controversy. We have the impression that we are gradually revealing more and more hints, much as in a cosmic detective thriller. Additional insights into the underlying principles of our universe are promised at every step. Consider scientific discoveries to be like exciting TV shows with new and unexpected revelations about the cosmos at each turn. That's all the information we have for you today. Share your opinions in the comments below. Thanks for watching another episode. While you're here, you can watch more space-related video.